Okay, I'm going to do a little graphing of trig functions, and we'll talk about it as we go. So there's four things we're interested in: amplitude, period, horizontal shift, vertical shift. You're not really going to be asked to identify the graph, although we typically deal with sine and cosine, tan very occasionally. And it's more about these shifts and translations you can make to them. So if this is my parent function, sine of x, okay, I start at 0, and I go up to 1, and I go down to -1. Right? And the distance between 0 and where I go all the way up, all the way down, and back to the midline, back to 0, is 2 pi, or 360 degrees. So amplitude of 1 from the center line starts at 0, goes down to -1, and it goes on and on forever. It's periodic. It's like waves. Let's see what happens. Let's start changing it. If I put a coefficient in front of the sine, let's see what happens. I changed the amplitude. I doubled the amplitude. So a coefficient greater than 1 will make our graph taller. Doesn't shrink the period, how frequently it occurs. See, still hits the peak at the same place, still hits the trough at the same place, still hits the middle line at the same place, still takes 2 pi to do all that, but it's twice as big. If I move that 2 in front of the x, I've made the graph twice as frequent. So here, start at 0, up to the peak, down to the trough, back to 0 again, right? But I did it in pi instead of 2 pi. So it takes the orange graph, the original graph, 2 pi to get there, takes me half as long. The bigger the coefficient, the shorter the period, the faster it moves through the cycle. Like, I can make it ridiculous. 9x, 10x. You get the idea. Okay. What about if I add something inside the parentheses? Well, then I shift over the starting point. I shift over where it starts, and it's a horizontal shift, right? So I moved the graph left just like I would in an algebraic function essentially by 1, right? Or by pi would be a better way to do that. So when I do it by pi, I've completely flipped the graph around, right? Where it's peaking here, it's at its valley here. If I do it by 2 pi, it'll match up again. Why? Because I shifted it one complete revolution, one complete cycle back. If I do it by pi divided by 2, it shifts it 90 degrees. And this actually is a cosine graph now. All right. Well, it looks like a cosine graph. And last but not least, if I add or subtract outside of here, I move it up and down. So let's kind of go over this together. What happens? Well, when it's outside, here's my parent function, sine x, right? When it's outside the sine, it affects the amplitude. When it's inside here, I wonder if I have a purple. This would be a good time for a purple. That's brown. If it's inside here, it will affect the period, how often things happen. If it's here, it'll be a horizontal shift. And if it's out here, it's a vertical shift. These parts in particular remind me quite a bit of algebraic functions. See, this is inside the function. The same thing's happening to x as is happening to this h, this horizontal shift. That's the same as horizontal shifts in algebraic function. Check that out if you want. Outside vertical shift. They in front, if you recall, if you put a number in front of x squared, coefficient other than 1, if it's bigger than 1, it'll make that parabola go really narrow, right? It's less than 1 really wide. It's not quite doing that. That's kind of more like the period function, but it does make it taller. I don't know. Different people have different tricks for remembering that. Do you absolutely need to know this? No, it depends on what you're looking for and what you're trying to do. Let's go ahead and jump into an ACT full screen problem. Okay, this is a pretty standard graph of trig functions question. They like to give you a couple graphs. One of them's a parent graph, and then one of them's had some changes to it, and they're going to ask you really generally about the changes. Good news is you don't need to know technically all that stuff we just went over. Okay? Don't need to know all that stuff we just went over. You just kind of got to be able to hazard your way through it. So familiarity is pretty good. Memorization is best, right? But that depends on what you're going for, what your goals are. But if you're familiar with it, you got a pretty good shot. Let's take a look. So let's figure out which is our parent graph, or a sine of x. Well, okay, this 0 goes to 1. Okay. Goes back down to 1. It takes 2 pi. Okay. So this graph right here is our parent graph, right? And then we got a sine of x plus b. Okay, some changes happen. It's taller. It's taller, goes up to 2. So I think because the amplitude was 1, right? Right? Is the amplitude of 1? Now amplitude's 2. We know that a is going to be greater than 1, but we could actually say a is equal to 2. B, that's a vertical shift. Well, it looks like it's starting at 0. If it's vertically shifted, it would start somewhere else. So I think B is equal to 0. Now, we can do a lot of marking off. After I got done with A, to be honest with you, I shouldn't have marked off, because you should always do that before you do a second part in case you don't need to. A, B, and C all have A less than 0, so those are out. And then E has B greater than 0. That leaves us with D, and D's correct. It is possible, if you have a little bit extra time, to work these in your graphing calculator just by putting in a parent function and manipulating the numbers a little bit. It's not ideal, but it's doable. These are not the most frequent problems in the world. Depends on what you're going for. If you like trig and you want this to be one of those minor topics in your basket, pick this one up. If you want that really great score, you're going to need all the topics you can get. Make sure you check out the stuff on unit circles. That's the stuff that's really important coming up later on in the videos.